graphic analysis, and then think about circuitry in the cerebellum. So, so it's 3 layered, it's not 6 layered, okay? It's 3 layered. And then if we're gonna output, it's gonna be the deep nuclei to it. And so here's a little picture of, if you look right in the upper right, these are the 3 layers of the gray matter of cerebellar cortex, okay? Cerebellar cortex. So we have a granule cell layer. These are really small neurons, and there's probably billions of them, okay? And then we have larger Purkinje cells in this layer, and then we have a molecular layer. And what happens is, let me draw this. So, we have granule cells, and they send axons up to the molecular layer, granule cell layer, molecular layer, Purkinje cell layer. Okay. And then they have little fibers that bifurcate, so they make like a T. So they go like right up to the surface of the cerebellum, and they make this T like this. Okay, see it? And here's another one. Okay, here's another one. And because there's billions of these, think about all these little fibers up here making these little, T formations on the surface of the cerebellum. If you look at the surface of the cerebellum, looking down at like here's the 2 hemispheres, it's not smooth. We end up with these little folio, and that's formed by those little T things. You know what I mean? These little T things, another T thing, T thing. You see how it build up folio, almost like the ridges of the hemispheres of the brain. You know what I'm saying? Okay, so that's what these form on the surface. And okay. Then we got these massive Purkinje cell layer. We have these massive Purkinje cells. And what they do is they have a fiber going up here, and it's talking to the granule cells, or the granule cells are talking to it. Okay, see it? In fact, it's like this. The granule cell is synapsing on this Purkinje cell, and then the Purkinje cell talks to the deep nuclei. And the deep nuclei output from the cerebellum. Okay, so right now we have a simple circuit. We got billions of granule cells. They're really small. They send fibers up to the surface of the cerebellum, and they bifurcate. They make like a T. Okay, and then these little T fibers of the granule cells, they synapse on Purkinje cells. Okay, so there's a simple circuit, and the Purkinje cell talks to the deep nuclei, okay? And the deep nuclei are the output cells of the cerebellum. So that's like a simple circuit inside the cerebellum. One thing that's kind of interesting is that Purkinje cells talking to the deep nuclei, this is inhibitory. Okay. So if that was the end of the story, think about it. Okay. If this was the end of this circuit story, if Purkinje cells are inhibiting the deep nuclei, and deep nuclei are the only way the cerebellum can talk to other parts of the brain. The cerebellum couldn't talk to other parts of the brain, right? This is like we're putting a brake on it, see what I'm saying? So we gotta add more circuitry in here, otherwise the deep nuclei are gonna be silent forever, and the cerebellum, despite this really cool error computation, wouldn't be able to do anything with it, you know what I mean? So now, remember, I just said there's all this kind of input coming into the cerebellum. And it's coming in two forms, okay? So one input is coming, so let's say, let's talk about input over here. So we got from a structure in the brainstem called the olive, because it looks like an olive. It sends these fibers into the cerebellum, and they do something cool. They climb up these fibers of the Purkinje cell. So these fibers are called climbing fibers. Okay. By the way, everything coming in also sends like a little collateral over here to the deep nuclei. Okay. These are excitatory. All right, so now we're balancing out this inhibition here. So we got these climbing fibers coming in, talking to the Purkinje cells, talking to deep nuclei from the olive. This is in the brainstem. Okay. Everything else coming in to the cerebellum we call mossy fibers. So let's do it here. No, that's it. This is all input. So other inputs coming in, and these guys go to granule cells. They're excitatory, and they also talk to the deep nuclei. And so we call these mossy fibers. What do I mean by other inputs? You know, like, I don't know, proprioceptive information from the spinal cord, like from muscle spindles or Golgi tendons, or from crane or gait, about what's your head doing. Right? So two kinds of inputs. Both inputs are excitatory. One, called climbing fibers, does something cool. It just climbs up these fibers of the Purkinje cells to reach the surface of the cerebellum. And then every other input, when it gets into the cerebellum, they call these mossy fibers, and they go in and primarily talk to the granule cells. Okay. But everything coming into the cerebellum also talks to the deep nuclei. Okay. So that's a simple cerebellar circuit for you. And, you know, imagine multiplying this by, you know, billions and billions and billions of cells, and think about the kind of computation you could do. By the way, if you do, I think I have a picture. Let me show you this. Look at that beautiful fluorescent, immunofluorescent micrograph. So this is, like what? Doesn't it look good? Blue and green, so nice. Too bad you can't see it, suckers. Okay. So, look at this. It's so beautiful, I think. So, this is called immunofluorescence. You know, I think we talked about this previously. We're using little fluorescent tags to light up neurons, and you can see there's multiple layers in the cerebellum, and this is a different kind of staining protocol where we're differentiating white matter from gray matter. And this, with this stain, white matter actually looks black. The myelin looks black with this stain. But anyways, by the way, we could add even more complexity into the circuit. There's other inhibitory interneurons, and you know, like basket cells and stellate cells. Let's not worry about that, but, so it's really complex. Just look at the arborization pattern, very beautiful, but, do I have another? I guess I didn't. So what I wanted to say is, the Purkinje cells in the cerebellum, that have that fiber going up to the surface, they can receive, one cell can receive up to, we think, 10,000, maybe to 50,000 or more inputs from granule cells. One Purkinje cell is talking to 50,000 potentially granule cells. So do the math. If you've got 20 billion granule cells and 50,000 of them can talk to one Purkinje cell, it's just insane the amount of computation that can happen, right? Just another picture of what I just drew. You can come back here for details. And so if you look here, remember, the only way a cerebellum can talk to the rest of the nervous system after it's done its kind of mysterious computation is via the deep nuclei. So there's the deep nuclei. Okay. So this output is to, the brainstem, and indirectly to cortex, and the spinal cord, and, whatever. Okay. And so what's talking to the deep cerebellar nuclei? Well, Purkinje cells are, right? And they're inhibitory. I showed you that. Okay. And Purkinje cells are receiving information from granule cells, right? And granule cells are making that T kind of function up at the surface of the cerebellum. That's excitatory. Okay. And then we have two major inputs coming into the cerebellum. We have climbing fibers coming in from the olive, from the brainstem, and they travel up. They climb up this little surface appendage, if you will, of the Purkinje cell. That's why they have that name, climbing fiber. Okay, and simultaneously they send a fiber over to the deep nucleus. So these are excitatory. Okay? So I just drew this. The other kind of input, any other input to the cerebellum, we call that input a Mossy fiber. And you can see it's coming from all different places, like the spinal cord, the vestibular part of the ear, whatever. And this stuff's coming in and going to the granule cells. Okay. Mostly, right? Question? Yeah.
Yeah. So why does the granule cell bifurcate? Does it talk to multiple Purkinje cells?
It's just a branching pattern that we observe. And I think it allows, by having that branching pattern, it allows one granule cell also to talk to multiple other cells. So it just allows for more complex circuitry. But how that works is beyond what I understand, kind of future in neuroscience. But you can imagine, right, like think about it the other way, okay, PJ. Remember, the input side of a neuron is the dendritic tree. If you have a really sparse dendritic tree, just a few branches, it can only receive a little bit of input, right? But if you have a dendritic tree that's really crazy branching, it's just anatomy, right? It can receive many more inputs, and so therefore you can get more complex circuitry evolving, right? So at either end of a neuron, if you have more complex branching, theoretically that allows for more complex computations to happen, even if we don't understand what that computation is. See what I'm saying? Or I don't understand what it is, which is more like, okay. So this is kind of neat. Just if you record electrophysiologically from those climbing fibers, the little guys coming in from the olive that are climbing up Purkinje cells, they have this kind of neat, it's called a complex spike pattern. Remember, I know you don't want to remember this. Go back to Unit 1. Remember action potential, okay? So if you record multiple action potentials, we would call that, a spike train. And if the shape kind of changes, we call that a complex spike. So that's what we see in climbing fibers. If you do the same thing in mossy fibers, you don't see complex spikes, you just see little simple spikes. So it's kind of different, if you will, like electrical signature, right? So the mossy fibers have a different electrical signature from the climbing fibers. That's kind of neat. So that's just from electrophysiology experiments. How do they do it? They stuck a microelectrode in these different neuron populations and they recorded their electrical activity and they asked the question, does it look the same? Does it look different? You know what I mean? Okay. So here, actually, okay, this is even different from what I've read. This source is saying, actually, one Purkinje cell can receive up to 200,000 different granule cell inputs, okay? I haven't read that before, but this source says that. You know, if you read enough textbooks and journal articles, you'll start to see it is not consensus. But so, it's a lot, right? Okay. So just a few little more comments about maybe what the cerebellum is doing, and let's just think a little bit more about what we have to do to move and stuff like that. You know, if you think about just like right now, I'm going to reach for my phone. There's like an acceleration as my hand goes to reach the phone, but then I got to slow down, right? So all that acceleration, deceleration, acceleration, braking, all that requires cerebellum, and you see problems with that, right? In those videos that I showed you at the beginning, we overshoot, like we didn't brake in time, right? The guy was trying to touch the finger, and he went past it. He didn't brake in time, okay? Or you accelerate right into it. You can't adjust the force. So that's kind of cerebellar stuff. Think about this too. All over the body, you know, different limbs, we have what are called agonist and antagonist groups, like biceps and triceps have opposite functions. Biceps flexes at the elbow, triceps extends. So to kind of adjust that too, that requires cerebellum. Agonist, antagonistic pairs. Yeah, so we think that climbing fibers coming up, the Purkinje cells are kind of helping the Purkinje cells learn how to respond to granule cells. You know, I think that's why they're getting that information from the olive. Actually, a lot of people think it's actually the olive in the brainstem where error computation is taking place between what did we try and do and what actually happened with movement. This is just showing you a little cartoon of where that olive is. If you know, take a neuroanatomy course if you want to be convinced that is there really a nucleus in the brainstem that looks like an olive? There is, and here it is. See, in cross section, it kind of looks like a little olive, right? And so here's and there's actually a couple olives in the brainstem. There's a superior olivary nucleus that you may not remember we talked about in the auditory system. That's the first place where information from both ears meets. So we use that for sound localization. But this olive is talking to the cerebellum, and we think it plays a huge role in that error computation. Again, what did we try and do with movement, and like what actually happened? Okay. This is kind of neat too. Think about like, you know, you're walking, your limbs are swinging like a pendulum. Or let's do it with the lower limb. You're trying to kick a football. Your leg arching towards the football is also like a pendulum. And again, you know, especially like if you're trying to hit the football with your foot, you have to adjust to the acceleration and deceleration precisely. If you hit the football with not enough force, it'll go like 2 feet, you know what I mean? And so that kind of acceleration and braking activity is cerebellar, requires cerebellum. Here's some funny words that we use to describe cerebellar dysfunction. So we talked about dysmetria problems with like the force and range. Again, you know, you want to touch your nose, you got to get all that stuff right. Problems with rapid alternating movement, dysautokinesia. I had a video. Do you remember in Parkinson's disease, one of the characteristics we see is a resting tremor? Okay, but I didn't show you this, but if you actually ask a Parkinsonian patient with resting tremor to move their hand, the tremor goes away. Okay? But in cerebellar disease, it's the exact opposite. You don't have a resting tremor, then if you ask them, say, to touch their nose, the tremor will get more intense as they get closer to the nose. Let me show you a video of that. So that's called an intention tremor. So it's the exact opposite of the tremor we saw in Parkinson's disease, right? Where is this? It's this one. Yeah, this guy.
In addition to rest tremor and postural tremor, is it one side of the cerebellar right nerve pathways?
He's doing a finger to nose test. And
the left side shows significant dyssynergia and intention tremor.
so on the right, it's pretty good. Now let's see left.
With the postural tremor, and in both the trajectory.
I just saw a tremor develop as he raised his hand. It wasn't there at rest. Now he's going to be asked to touch his nose. And again, you see the tremor kick in right as he gets closer to his nose. And he can't hold on his nose very well. So that's
Tremor can also be seen.
so we call that an intention tremor. Okay. You can have changes in muscle tone because it turns out like cerebellum, as you might expect, exerts a control on our stretch reflexes that we talked about in Unit 2. But we don't see paralysis, weakness, okay? So that's a real big distinction. And then of course ataxia, right? Discoordinated. And what, imagine if you're, that walking test we talked about that police do. Imagine if you had, how you would compensate, one, if you had too much alcohol or you had ataxia, you probably spread your feet wide, just so you have better balance. That's what patients do. So they end up with a wide gait so they don't fall over. Otherwise they just don't have enough control if their feet are too close to each other. So that ataxia is what we see with damage to that middle vermis, and we're going to compensate by putting our feet wide. What if we damage the vestibulocerebellum? Then we'll see these classic cranial nerve things like vertigo, dizziness, nystagmus. I'll show you a video of nystagmus. And if you damage the lateral parts of the cerebellum, this is where you see really more complex phenomena, because this is the part of the cerebellum that's like helping coordinate sequences of movements, right? And so here, just some graphical representations of things that you see. So this is a person with a right cerebellar hemisphere lesion. Where would you expect to see the symptoms? On the right, right? Because it's not a crossed circuit. And the patient is told to clench both hands at the same time, and their hands clenched, at different times. Okay. They're told to touch a dot and then touch their nose, and they kind of track the path of their hand as they're getting to the nose, and you can see it's not a straight path, right? Whereas for us, no cerebellar damage, just a smooth, straight path, finger to nose. And then for most of us, if we're asked to do a rapid alternating movement, it's just kind of smooth, like right here. I'm pronating, supinating, pronating, supinating, pronating, supinating. But with someone with dysdiatic kokinesia, you can see it kind of breaks down. They can do the rapid alternation, but it's not as smooth. Okay. All right. So at the end, we put it all together. Let's just end this motor unit. You're like, thank God. Okay. You damage corticospinal tract, you have problems with distal muscles in particular, and weakness, paralysis, fine movements. Okay. All right. You also can see changes in reflex activity, which we talked about. You damage basal ganglia, you either can lose movement, we call that bradykinesia, brady means slow, or you can end up with hyperkinetic movement disorders like Korea, we have, right? Involuntary movements, sometimes they look dance-like, or maybe, remember, hypolismus, explosive movements on one side of the body. And then you damage the cerebellum, we see a whole different kind of symptoms like discoordination, things like that, okay? So now, we have a little time. let me just show you, let me show you nystagmus if you've never seen this. Actually, let me show you Korea. Alright, did I show you Korea? Tuesday? There's all kinds of nystagmus. Involuntary oscillatory eye movements. This is just one example.
This video is just to demonstrate latent nystagmus.
Okay.
So right now, we're looking, Lainey is looking through her left eye, and her right eye is covered by my TV camera. So right now we've got
So that movement you just saw there, that's not intentional. That person's not trying to move their eyeball. Okay. By the way, alcohol also can trigger, changes in cerebellar function and vestibular function, and cops will look for that too. If they suspect you of drinking and driving, they might ask you to, they might look at your eyes, and what they're looking for is nystagmus. Nystagmus will come out too with alcohol consumption. But it's really characteristic of brainstem damage or cranial nerve 8 damage or cerebellar damage. You get these involuntary oscillations of the eyeball, okay? All right. So, okay, got a few minutes. What do I want to do? I want to draw direct circuit basal ganglia again, but I just want to talk about it a few more minutes, just so we're not confused or less confused. Okay. So